current by the magnetic field. Well, however, magnetic field is not something you can really touch or you can really measure it. It's better way you should say is by the magnet. To me, how you describe the magnetic force, you just need to think about, if I remove the magnet, do I still have the magnetic force? And then the answer is no. If there is no magnet around the current, there will be no magnetic force. Therefore, we can describe this magnetic force. Let me write here. This is a magnetic force on current, and then this is a force by magnet. Well, applying the Newton's third law, then it's just like a grammar. We just need to say, I have a force exerted on A by B, and now it becomes on B by A. That's it. Doing something secretly. Anyway, now I think it should be okay. Now, so what is the reaction partner? Will be another force, and then it is of the same nature. Magnetic force, and then on A by B, on B by A. So therefore, it should be on magnet by current. So therefore, in the sense that you have the magnet pushing the currents up, while the current is actually pushing the magnet as well. And according to the Newton's third law, these two forces should be in opposite direction and equal magnitude. So therefore, well, in reality, usually what they have is that we have like a bar magnet like this. And then we have this bar magnet on this, and therefore there is actually a downward, let me draw it properly. There is a downward magnetic force exerted on this magnet, SSF. And this force turns out can be measured because you can just put this bar magnet on a, electronic balance. Then it is just like you have someone push the magnet a little bit down. Then when you put the whole thing on a electronic balance, then the readings of the electronic balance would change. And then just based on that, we will be able to measure the force on it. Just put one example. For example, before I turn on the currents, I may have the readings of the electronic balance will be just measuring the weight of the bar magnet. Let's say, suppose initially it's like 100 grams. And then now, as I turn on the currents, then the readings of the electronic balance will increase. Let's say it becomes 125 grams. Which makes sense because you just imagine you slightly push the magnet down, then the reading of the electronic balance will increase. Well, that means because of the magnetic force, there is an extra force causing this 25 grams in the readings. Well, 25 grams means 0.025 kg. And then that means in order for the electronic balance to read this 0.025 kg, you're supposed to exert a force of mg, Wmg. So therefore it's 0.025 times, let me use 10 for example, then you have 0.25 Newton. So therefore we can deduce that, therefore the magnetic force due to the presence of the current in the wire is equals to 0.25 Newton. Should be like this. Which is quite important because in this one is quite a good example that many physics teachers like, is that because this tells you how to measure the current here. It's basically impossible to measure the current exerted on a wire like this. How can you measure that? I just have electronic balance. Or maybe if you recall, I have something called spring balance, that you have a spring and you can pull to deduce the force. But magnetic force is so weak. Well, we're using very small currents to prevent overheat. So the magnetic force is so weak. So how can we really measure this thing? Well, I cannot. I can only measure this. So we need to convert, or we need to connect these two forces, and we are using the Newton's third law. Okay. Now, so after this, then we can talk about more about the forces. The thing about forces, we have talked about last time. We talk about how to use the head to tail to find the forces. We also talk about how to use the component to find the forces. This is part of chapter 7. And then the remaining part, inclined plane. Then another one, this will be like, I think it's chapter 7. I remember. Chapter 7. This is about so-called more about forces. Let's look at some interesting cases. For example, one interesting case is the so-called system of mass. That in the past period question, we like to test it a lot. For the system of mass, what we are referring to is that you have two masses, m1 and m2, and they may be connected to each other. So therefore, they will have the same kind of motion. It is. And then we need to, for example, just like before, we always have to study the free body diagram. So therefore, for this, you will have a free body diagram of, let's say, mg. This is the downward mg. And you will also have a tension, which is going up. While for the free body diagram of the M1, then you will have the normal contact force exerted on M1, and you have the, this will be lowercase m. So this is the capital Mg, and this will be the lowercase, we just call it Mg, and you will have a tension here. So this reminds us first of all, that the two tension will be the same. Because we assume that the tension is, as long as the tension is on the same string, then we will have a uniform tension. So this is actually one properties, which is uniform tension. As long as these two tension is about the same string. So it's on the same string. Like this. After doing this, then what else we need to do for this so-called system of mass is that we have to understand that they have the same magnitude of acceleration. So the mass on the bench has an acceleration going in this direction, so it has to be A. And then for the capital M, then the acceleration is the capital A, like this. So therefore, in this sense, the two directions are not, the two accelerations are not the same, because one is going to the right and other one is going down. However, they have the same magnitude. This is a very important feature for the question relating to masses. The two masses must have the same velocity, must have the same acceleration in magnitude, because they are connected. If they are not connected, then there's no point to talk about two masses in the same questions. So this will be used. So the next part will be just very standard. We will say that I have R1 equals to mg. This may be useful, maybe not useful, I don't know. And then the remaining T is the resultant force. So like last time we do MA. And then for the capital mass M, then we will have one equation only, which is mg minus T will be the resultant force, and then this will be equals to MA. Like this. Now, so we have to we make use of the fact that they have the same acceleration, so you don't need to have MA1, MA2. We just use the same A, same acceleration. After this, then we can solve the problem depending on what they ask. One very common way is to solve the acceleration, and then in that case, we eliminate the tension. So therefore, we just use T equals to MA, and then we substitute into mg minus T equals to MA. Yes, substitute into this one, MA. So therefore, we will have mg minus T equals to, minus T is MA, and this is big M, small a. Therefore, we have A equals to mg over small m plus big M. I think you can see by just moving the M to the other side. I think one mistake that some students can make is on this part. Let me use the use another color. This part here. Some students, they will take T minus mg, but it's not okay, because for this mass, M is accelerating downward. So the mass M has a preferred direction of motion. It's accelerate downward. Therefore, we should take the downward force to be positive. So that's why we choose mg minus T instead of T minus mg. Some still will have the idea, say, I use mg minus T because I think mg is bigger than T. Well, I can't say it is wrong, but for this kind of like a 50-50 situation, it's very hard for you to determine, because sometimes maybe you cannot tell whether mg is bigger than T or T bigger than mg. That's why I do not prefer students to answer in that way. I would prefer the student to understand that, this mass, it has a preferred direction of positive, because this mass is accelerating downward, so therefore I take downward as positive. This will be more useful as an examination skills. Then other possibility will be so-called using a pulley. So pulley will be something similar, but I don't think I want to go into details. So just to illustrate that the system of mass can be asked in many different ways. More examples. One will be you have a pulley, and then you connect this to a ceiling, and you have a mass on one side and a mass on the other side. Or another example is you have the two masses to be pulled by a person like this. And then another example may be you do not have a level side bench, but you may have a inclined plane. sometimes you have something like this, pulley, put it here and then put it here. But no matter how, for all kinds of situations like this, you can always solve using the same method. Namely, you draw the free body diagram of the two masses, and then you you need to apply the fact that they have the same magnitude of acceleration, and you got the equation and you solve it. So these are just more examples. Now, inclined plane. Inclined plane is a very classic types of question that you will encounter when you deal with forces. Inclined plane. Then this is a very standard type of question that you have an inclined plane, and then we define this as the angle of inclination. And then you have a mass. The simplest case would be that it will be no friction. So you just need to have the normal contact force, R, and then the mg, which is pointing down. And then the main idea here is that we don't resolve the forces to vertical or horizontal. Because somehow, although in the past, for example, in the example we did yesterday, like this, we say that, T is troublesome. In the case, maybe we call this, and you have a ball connected to the ceiling of a car, and then because the car is accelerating, so the string has subtended an angle with the vertical line. And therefore we got a tension, and yesterday we say that this tension is problematic because it is not vertical nor horizontal, so therefore we break down the tension into vertical and horizontal component. This is very common. For many situations we solve it this way, even including circular motion. However, not all the case. Inclined plane will be the scenario that you should not resolve the force into vertical and horizontal component. Why? Well, one major issue is, for this case, or many other cases, the acceleration of the mass is horizontal or vertical. For example, in this case, the mass is attached to the car. So when the car is accelerating, it can only be accelerating to the right or to the left, meaning that the acceleration of the mass has to be horizontal. So therefore, the acceleration is horizontal, then this again go back to the same thing. The question already has a preferred direction. Horizontal is a direction preferred by this setup. So therefore, we choose horizontal and vertical. However, for inclined plane, will this box or will this mass accelerate horizontal? No. It is going to accelerate downward in this direction. So therefore, it doesn't make sense to use vertical and horizontal anymore because the question has a preferred direction, which is along the plane. So therefore, the main idea we use here is we do not resolve the force into vertical nor horizontal component, but we do along the plane and perpendicular to the plane. These are the two directions that we want to resolve to. So under this situation, or under this context, the normal contact force is in fact a good force because this force is already perpendicular to the plane. The problematic force is mg. So therefore, we need to break down mg into vertical and horizontal component. And then the trigonometry will tell us that if I have the R going here and you have the mg going down, you put back those triangle, then you will have these to be theta. So therefore, the normal contact force is perpendicular to the plane, so that's good. But the mg has to be resolved into mg cosine theta and mg sine theta to be the component perpendicular to the plane and along the plane respectively. Now, so this is what we have. And after this, then we can carry on the same analysis. So intuitively, or based on the fact that the box only move along the plane, we will say these two are equal. So therefore, R is equals to mg cosine theta. While on the other hand, the only resultant force is the mg sine theta. So we got the resultant force equals to mg sine theta. And we know that resultant force is equal to ma. So therefore, we just put ma to be the resultant force. Ma equals to mg sine theta. So A equals to g sine theta. You remember this? This is actually a very classic result. The DSC, they suppose you to know that the acceleration of the inclined plane is given by g sine theta. But of course, this is only true when there is no friction. So that's why the key term like smooth plane, no friction, things like that, we have to pay attention to that. Well, as we noted that this is a constant acceleration. This is a constant. So in other words, we can use the kinematic equation. So Sufat. The four equation we described last time can be used in the case of the inclined plane. Well, then how about if there is friction? Well, this is the case that there is no friction at all. So this is like the smooth inclined plane. This part is a smooth inclined plane. But if you have a rough inclined plane, then what will be the case? Well, it's actually the same. You just again study the same thing. Angle of inclination theta is here. You have the box. And then again, the normal contact force is here, R and mg. But this time, if it's rough, that means there will be friction. But what is the direction of friction? Well, it depends. Is this mass at rest, or is this mass moving? If this mass is moving, then it's very easy. The direction of friction is just opposite to the motion. So let's suppose this is one possibility, motion. It is going up along the plane. So therefore, this is the direction of motion, the velocity. Then in this case, the friction will be opposite to this velocity. Then we can say, the friction will be going like this. Well, friction is a good force because friction is along the plane. So therefore, we do not need to do anything on the friction. The only troublesome force is still the mg. So therefore, we do the same as before. Then we will have R and F, then and break down the mg into mg cosine theta and mg sine theta. As before. And then similarly, as before, we will see that R equals to mg cosine theta, and then the resultant force in this case will be F plus mg sine theta. Then resultant force equal to ma, therefore you have the new formula for finding the acceleration. Like this. Okay. Well, what if the motion is not going up? What if the motion is going down? What would be the change? F goes up. Yes, then the F goes up, so therefore the direction of F will be negative. So with negative sign, you have a negative sign if the box is going down. Well, then the last scenario will be when the mass is at rest. Beta here, and then we have R, mg, and these two has to be always there. Well, the motion here is at rest, no motion. This is also similar to a question that I think just yesterday, Marcus asked me about it. Is that how do we really find the direction of friction? Well, and I also explained to him that, well, if the object is moving, the friction is very easy to find. The direction of friction is opposite to the direction of motion, just like we did here. But if the object is at rest, then how do we determine the direction of friction? In this case, it's not very obvious. Sometimes I would say, sometimes I would say you need to use some intuition or some common sense, or the common sense or the intuition you developed for after you study so many years about physics. So what to do? Because at rest has no particular direction, so therefore we cannot really base on the motion to tell the direction of the friction. We need something else. The thing is, we pretend that there is no friction first. That, if there's no friction, and I will just have the normal contact force, and I have the mg here, and then we say that mg is troublesome, so I need to make mg into mg cosine theta and mg sine theta. So up to this point, then you find out that there's a problem. That for a given free body diagram like this, is it impossible for the mass to be at rest? Because there will be an mg sine theta here. Although r and mg cosine theta, they cancel, but mg sine theta will be the so-called unbalanced force. But we learned from Newton's first law that the system is at rest, so the resultant force has to be zero. This is a requirement. So in other words, I need a force to balance an mg sine theta. So it is under this context or under this idea, we put back the friction into it. So the friction exerted on the inclined plane, for the case that the box is at rest, the friction is pointing up. The friction does not move the box. The friction is only there. Its primary function is to eliminate or to balance the mg sine theta. Because we know that if you don't have that friction, then the mg sine theta will become a net force, then it will violate the Newton's first law. So it's this idea that how we determine the direction of friction when the object is at rest. You see, this kind of logic is very similar to the Newton's first law example we did before. It's always the case is that I use the Newton's first law to deduce the direction of the remaining force we have. Last time we said, oh, you just have these three forces, and then using the Newton's first law, then we realize that, oh, I need a fourth force. The fourth force here should be there to balance R2. Because R1 and W, they cancel, but R2 is the remaining force. I need to get rid of it. So I rely on the friction to balance this R2 so that the resultant force is 0. Okay. So this is the inclined plane. After inclined plane, then we just have moments, and the moments will be about the turning effect. What's the formula for moments? Force times perpendicular distance. First of all, we definitely need to memorize this definition. Force times perpendicular distance. And in full term, it should be perpendicular distance from the pivot. And I think, and then the unit, don't forget the unit. The unit is in Newton and it is in meter. Therefore, the unit of moment is Newton meter. And it turns out that moment is also a vector because it can be clockwise or anti-clockwise. This is important because we're going to use the principle of moment and using the principle of moment, we need to tell that the total clockwise moment equals to the total anti-clockwise moment. Now, I think the perpendicular distance is the only non-trivial part. The example I get is, I think very similar, is that, let's say you are pulling a luggage. Like this. And then, therefore, there will be the weight mg, and then there will be a pulling force in this case. This may not be that good. Maybe maybe I have a pulling force which is let me think about it. If I draw this, it does not work that much. Maybe like this. So you have two forces, and the force is like this: Fx and Fy. Like this. And you will see later why. Well, of course, usually on the handle, you just exert one force. But now what I did is I break down the one force into a horizontal and vertical component, and then I will later argue that which one should be bigger. Suppose 45 degree right now. 45 degree right now. Now, in this case, where's the pivot? Well, the pivot will be located here. So basically, you just imagine if you let it go, then it will turn. When it turns, there must be one point on the object that remains at rest. And that point will be the pivot. So therefore, this is the pivot. And then, therefore, three forces here, so we can talk about three moments. Oh, actually, there's one more force. There's actually one more force in this three-point diagram. What is that? Normal contact force. Exactly. Contact force. So, therefore, there's a R here. Okay, so after this, there are four forces. I try to tell you what I will be thinking when I'm doing this kind of question. There are 4 forces in the free body diagram. It means that there are 4 moments. There are 4 moments. So, therefore, you should kind of reserve your understanding that, there will be moments due to R, there should be a moment due to mg, and then it should be a moment due to fx, and there should be moments due to fy. Because there are 4 forces, then there should be 4 moments. And let me give you some number. For example, I call this as A, and then I call this as B, and then I call this as C, and then I call this as D. Like that. Then, how can we calculate the moments due to these 4 forces?
Is it moment due to R equals 0?
Why?
Because on the pivot.
It's on the pivot.
The perpendicular distance is 0.
So the perpendicular distance from the pivot is 0. Yes. So the moment due to R should be calculated by the normal contact force times the distance of R from the pivot. But the distance of R from the pivot is 0 because the R is exactly on the pivot. So therefore, this normal contact force does not give you any moments. Then how about mg?
AMG.
AMG. Why AMG?
Because the perpendicular distance from the pivot to MG is A.
So the force is of course mg, because you need to have moments here. Moments equals to force times perpendicular distance, and therefore, of course, we use mg. But the thing is, you need to multiply the perpendicular distance of mg from the pivot, and then at the end, the answer is actually A, not C. This one, the way we do it is relatively simple. It's just if you want to find the perpendicular distance, wait. I want to do this. Yes. And then, let me yes. If you want to find the perpendicular distance of a force, first of all, you locate the pivot. The thing you only need to do is just to use a ruler and then try to extend the line parallel to the force. You can always do that because a force is a vector. You just draw a longer arrow. And once you did this step, as I suggest you to do, then you immediately see a point, the pivot, and the line. So therefore, the perpendicular distance now becomes obvious. We need to choose this distance. Because this distance is good because this distance gives me a 90 degree. And therefore, this length is just the same as A, not C. So you are responsible to use the correct value for the perpendicular distance, and therefore you need to know well how to find the perpendicular distance. So because of this, then Fx, the moment of Fx and moment of Fy should be fine. Alrighty. Kathy, can you tell me which perpendicular distance should we use for fx, b or dot, d for dot, this one, fx for b, right? Extend this line, then therefore the distance we should use to be the vertical distance here. So therefore times b and then fy times d. Like this. So therefore we have 4 moments, but the first moment is 0 and we only have 3 more moments. And after that, we need to find the direction. So the direction of the moment, the moment due to mg will be clockwise, because you can imagine this point is fixed, then this one this one try to pull down the whole luggage. So therefore it's clockwise. And then this Fy will try to turn the luggage this way, so it will be anti-clockwise. And then Fx will try to turn the luggage this way, so it will be clockwise. So therefore, using the so-called principle of moment, then we should expect that you have mg times a plus fx times f equals to fy times d. So this will be the application of the principle of moments. Okay. The total clockwise moment equals to the total anti-clockwise moment. And this is how we get the equation, and then we can base on this equation to make some prediction. Now, for example, let's say if for example, let's say what happens. What would I say? I want to say B and D. B and D. I know. Yes. So what can we do here? Now this is the use of the principle of moment. And then with the question may ask, what happens if I what happens if I am pulling this this luggage so that it is pulling at a larger angle? For example, this angle, theta. What will be the change? Oh, it is. I think let me think about how to ask it properly. Let me do this one. Just do it this way. Now, this is the result of we obtain from the principle of moments, but it is not the end, because we did not talk about the Newton's law yet, about the F equals ma. So what I want to do is to argue that Fx should be 0. Let me make it easier. I think I make it complicated. Now let's say, look at this diagram first. Can this luggage be at rest? No. Which direction will it accelerate? To the right. Because the Fx I put it there is the only horizontal force exerted on the luggage. If I'm going to just let the luggage to just you hold the luggage but not pulling it, then you should not have the Fx there. So therefore, let's say suppose right now I only study the case when the luggage is at rest. Suppose at rest. Then I will have Fx equals 0. This one actually comes from Newton's law. You may say it by Newton's first law. Let me put it in details. So suppose at rest. Therefore, the Newton's first law tells you that the resultant force is equal to 0. So therefore, I should have horizontal. So therefore, the free body diagram, which is just F, Y, and then R, and then mg, and then Fx. Then I will have R plus Fx equals to mg, and I should have Fx equals to 0. So when we use this into this formula at the bottom, then at least I can immediately find out that Fx is 0. So therefore I will have mga equals to Fyd. Because Fx is 0 already, I just cancel. This is just here. Now, this step. Then that means the total clockwise moment is just produced by mga, and then the total anti-clockwise moment will be Fyd. Now this is simple enough, we can make some prediction. I kind of like to really, this will be too much for a DNC to make a prediction. But this one, now the prediction I want you to get is, after all this effort using moments, principle of moments, and also knowing that Fx is 0, I got this one. I want to know what happened if I have a longer angle. And because you remember, this length of this angle can be sometimes like this, sometimes like this. And you can have different parts of different length. What if this length here is long? What happens to the force I
FYD is bigger.
Fy will be bigger.
Yeah. FYD changes to FYD2, which is bigger.
Okay, so what? Why this guy is so loud? My 611 is basically like. Why FYD is larger?
Because D increased.
D increase, okay? D increase. So this whole thing must increase, right? Provided that Fy is unchanged. But this whole thing equals to M. This whole thing is equal to MGA. Is MGA, can MGA increase? No, because M no change, A no change, G no change. So therefore, this whole thing is unchanged, but D increase. Then
FYD is bigger than MGA.
Fy need to decrease.
Decrease.
Yeah. Because this is constant, this goes up and this
Wait,
goes
are
up.
we saying assuming it's still in equilibrium? Because I know we're gonna talk about it turning.
Hey, very good question. although just looking at this, then I will have to just say Fy decreases, but can Fy get smaller? Will a smaller Fy break the Newton's first law?
No, but like, if Fy remained the same, right, and it turned into like moments equal to like Fyd minus mga. That's what I was thinking just now.
Which part? Why minus
I misunderstood what you were asking because I thought it was like you're talking about if it was no longer in equilibrium.
It's in equilibrium.
It is in equilibrium, is what she said.
Fy will be smaller. If Fy will be smaller, it may affect this part here. That if this is smaller, mg is the same, then you have a larger normal contact force. So in other words, when we make the handle longer, you actually need a smaller force to make it stable, but the normal contact force is bigger in the sense that actually the wheels actually experience a larger force. Oh, something like this. I'm not sure. I think it's not too difficult. I think it's okay. This is okay. This is a like a DSC question. Being able to arrive at this step as a DSC is not. But I don't think we need to make any qualitative conclusion based on this is so many variables. The fact that there's so many variables, we cannot make a conclusion. That's why I said, okay, let's suppose Fx is 0. Sx actually should be 0 if this whole thing is at rest, if it's not accelerated. This question can be talked about acceleration as well. You're pulling the luggage and then at a certain acceleration, or you have the Fx given, then you can find a horizontal acceleration, use a super or whatever, I don't know. But maybe the part B is at rest, then you can assume there one, then this one you are expected to make qualitative conclusion. And the last comment will be, well, because this part is complicated, so many variables, Fx variable, Fy variable, B variable, D variable. B and D are variable because when you turn like this. That's why when you are holding the luggage and accelerating, it's actually, if the mass is heavy, so this term is big. This term cannot be forgotten. Then it's actually very difficult whether you should like put it up or down, put it up or down. You make it force too big, then you can't like do it this way. You make it too down, then you might fall down. So this equation actually captures the thing when you're holding a very heavy luggage, so this term is important, then this variable here, they struggle, they go up, go down, go up, go down. Well, I think we take a break first. After 10 minutes or maybe 5 minutes, and we talk about magnetism.